wrote the paper in Nature or the J-Phil mag, and it took about a page and a half to describe what he had done, and he had done it all in a little tube of this sort of size. Of course, today we use much bigger analogues of these little tubes. We call them electron accelerators. We'll meet them later. But to show you also how the sociology has changed, this is Thomson's analogue today. If you can just move the slide on, Jeff, thanks. So this is a team who are working on one experiment at an accelerator in Germany called HERA. It is the world's most powerful electron microscope today. It consists of a 4-mile ring which takes electrons whirling around in one direction and protons, the heart of the hydrogen atom, going in the other direction and hits them head on to each other. And that is a much bigger enterprise than this. And as you can see, it requires a lot more people to do it than just one. And what's more, this is a colour photograph, which shows you other things that have changed. So that is really where we're going to go. Now let me set the scene to get some idea of what it is that we're trying to chase. I thought I would just look for a moment or two at the sort of size of things. The world out to the very big universe on the one hand, and then the world down to the atom and beyond on the other. So like the typical scale of things like us, I mean, of the order of a metre in height, I mean 2 metres, but of the order of 1 metre, or 10 to the 0 metres. The size of the Earth, the diameter of the Earth, is about 10 million metres, 10 to the 7 metres. So 10 million of us lying head to head would go right the way through the Earth. The size of the Sun at 10 to the 9 metres means that the Sun diameter is 100 times or so bigger than the Earth in size, in diameter. The orbit of the Earth around the Sun is about 10 to the 11 metres. So that's another factor of 100 compared to the size of the Sun, which is in turn a factor of 100 compared to the size of the Earth. A light year, the distance that light will travel in a year, is 10 to the 16 metres. The size of the Milky Way galaxy, where we live, is of the order of 10 to the 21 metres. So you're beginning to see a big Earth's orbit to a light year is 5 orders of magnitude, a light year to the Milky Way is 5 orders of magnitude further. Clusters of galaxies, even 2 orders of magnitude bigger, superclusters at another order of magnitude, and the visible universe, meaning the deepest that we can look towards the Big Bang with the most powerful telescope today, about 10 to the 26 metres. So those numbers begin to mean nothing at all, other than they're very big. What I wanted to do was to bring out the fact that although it's hard to comprehend the actual numbers, the differences of scales you can get a feeling for. Know that the size of the Earth to the Sun's size is 100, the Sun's size to the Earth's orbit another 100, 5 orders of magnitude to a light year, another 5 orders of magnitude to the Milky Way. You're getting the feeling of big scales but going in separate chunks. Let's go in the other direction, and we go into the world of the very small, which is a world that often you think is beyond vision, but I would say it's beyond normal vision. We can't see anything with our eyes that's smaller than about a tenth of a millimetre or a bit less than that, 10 to the minus 4 metres. Now, compare this with the size of bacteria, which is about an order of magnitude or so smaller or thereabouts than what we can resolve with our unaided eye. You need to have instruments to do that. The wavelength of visible light, by that I mean the light that we see with, the rainbow of light, which is just a single octave in a whole range. There's like, imagine a piano, and you could only hear 1 octave in the middle. Well, that's what the electromagnetic spectrum is like. There's electromagnetic radiation spans over many, 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 many octaves. There's radio waves down there, there's infrared radiation just there. The single octave in the middle that we call the rainbow is what we see with. And then there's ultraviolet and X-rays and gamma rays out there. But the moment you can get out of the rainbow with our eyes, you can start looking at things much smaller than our unaided eye can see. So the wavelength of visible light is 10 to the minus 6, 10 to the minus 7 metres. The size of atoms are much smaller than that. The size of the atomic nucleus is 4 or 5 orders of magnitude smaller still. The size of quarks and particles like the electron, well, we don't know what their size is. All that we know is that their size is smaller than 10 to the minus 18 meters. That's another 4 orders of magnitude. So quarks compared to protons are like protons compared to the hydrogen atom. It's very, very empty down there. So what hope do we have of being able to get in and see if the quarks do have a size? And if so, whether they're made of something else? That's the current frontier, and that's where we're going to go today. How do we go and do that? How do you actually see things? How are you seeing me? Well, this is what you do. I mean, if you want to see that Bondi Beach surfer there, you have to shine some light on it, and then the light is reflected into your eye. So today, we're seeing each other because the light shining on me, you pick it up in your eye. In the jargon, you need a beam of radiation. It might be light, it might be electron beams, it might be other particle beams. They shine on the object that you're interested in, and then this radiation scatters from that object into something called a detector, of which the eye is a particular example. So suppose that you want to go and look at the atoms that that person is made of. How do you do it? I mean, can you get a magnifying glass and go and look very, very closely? The answer is no, not if you're using radiation that our eye picks up, because a magnifying glass makes things bigger. But what we're trying to do is to be able to resolve things that are very small, to be able to look with such precision that we can separate one small distance from the next. And the problem is that you're limited with ordinary light, just like a wave. Well, let's look at the next picture to give an illustration. To show the relative scale of the wavelength of green light right there in the middle of the rainbow with the size of an atom, you've got this very long wave, 10 to the minus 7 meters, and you're trying to scatter it off an atom that is 1,000 times smaller than the wavelength. Now, it's hard to imagine what would happen, but if you think of water and ships, you can see the analogy. If you have got a very big oil tanker, and you've got waves that are rolling along, when the waves hit the oil tanker, they scatter from it. And so if you had some detector over there, like, say, a piece of cork sitting on flat water, the scattered waves would arrive, and the cork would start bobbing up and down. So that cork bobbing up and down would tell you that the waves had scattered from something. And if you were very clever, with lots of pieces of cork around, you could work out that they scattered from an oil tanker. The critical point being that the oil tanker is much bigger than the wavelength of the water that had scattered from it. Suppose instead of the oil tanker you had a very small boat, much smaller, let's say this size, than the wavelength of the water. Then the water waves would just roll past, that boat would bob up and down, it wouldn't scatter the waves at all. In a sense, it would be invisible. So the key thing in the case of scattering water, and it's the same with scattering light, or scattering any wave, is that to see something, that something has got to be bigger than the wavelength that you're using. And that is now, you see, the problem. That light waves, which are like 1/10 of a millionth of a meter in size, are much smaller than me, so I'm like the oil tanker. They scatter off me easily, and you can see me. But they're huge wavelengths compared with atoms. So they don't scatter off atoms, and the atoms are effectively invisible, like the little boat. So what you need to do is, instead of using the rainbow of light that our eye is used to, you need to be able to use light of very much shorter wavelength, wavelengths of the order or smaller than the thing you're looking at. Now, you can go into the ultraviolet region where the wavelengths are smaller, into the X-rays and gamma rays where the wavelengths are very, very small, and you can start seeing smaller and smaller structures. The trick which we mentioned last week in Dr. Gore's lecture was to use electrons as your source of the beam. Everything is waves. This is the great discovery in quantum mechanics in the 1920s. Not just light, but everything. Atomic particles act like waves. Electrons act like waves. And the beautiful thing about electrons is they're electrically charged, and so you can speed them up and slow them down, you can control them. And what quantum mechanics shows us is that, if you like, the higher the speed, or technically the higher the momentum of your electrons, that's what the P is, the wavelength is inversely proportional to it. So the bigger the momentum, the smaller the wavelength the electron beam will have. So if you speed the electron beam up, the wavelength that it acts like gets smaller and smaller, until eventually it's so small it can scatter off atoms or other things. And so that is the idea, that you imagine having electron beams whose waves are so small in distance that on the scale of that, the atom is now big, like the oil tanker, and it becomes visible by scattering the electron beam. You've got to detect the scattered beam and interpret what it means, and after some work, you can work back and see what the shape, if you like, of the thing that you scattered from is. That's the basic idea. So let's look first of all at some images. How do we turn this off? That's way. Okay, right. Last week, Bryson Gore tried to show a video of an electron microscope. What I've got here is a series of 4 or 5 slides, which I may have shown before, but it's always nice to see things again, of an electron microscope image of a pinhead with improving resolution. So the first picture, you can see the head of the pin there. The sharp pinhead that you feel pricking you is actually already beginning to be quite sizable. To remind you of what Dr. Gore was telling us last week, the idea here, this is a scanning electron microscope which is scanning the electron beams over the pinhead and then feeding the picture into, if you like, the TV picture, and there you see it. And what we're going to do next is to select a little area in here and scan the electron beam over that and feed it into the same picture and see what happens. Let's go to the next one. And so it's looking at it with improved resolution. You can begin to see the bacteria very clearly on the pinhead, and if we go to the next picture, the bacteria begin to look like fish fingers now. And these are E. coli. If we go on to the next picture, we're now getting down to the level of you're seeing the strands of DNA, and this has been coloured by an artist, so it is clearer. And I think there's maybe one more. Yes, that's as far as we go. So you're getting down to the level of seeing molecules with an electron microscope on a benchtop. It's not a huge device we're talking about. This is a relatively small size electron microscope capable of probing down to distances of the order of molecules. So can we just go to the next one to make sure it's a blank? Good, that means I am at the right place in the talk. Lovely. So we've seen that story, and that's taken us down almost to the level of atoms. Now, the idea of atoms was around long before even the last century. I have to remember we're in the 21st now. It was only at the end of the last century when Thomson discovered the electron using his little tube that was the first clue that atoms indeed are made of smaller stuff, namely electrons which are negatively charged, and something which carries the positive charge. We know today what the something is. It's the atomic nucleus. But we know that courtesy of Rutherford. So let me go down to the next slide, which is going to sort of give us the punchline, but it will help us show us where we're going. This is the modern picture of the atom. This has been known since, well, 1970 really. I mean, the nature of the atom and the fact that it has an atomic nucleus has been known since earlier than that. We'll take it one step at a time. So the atom has negatively charged electrons whirling around on the outside, and that's what we see up in the top right-hand corner. As far as we know, the electron is, well, the electron, if it has any size, it's smaller than we can yet probe. As far as we know, it's fundamental to the best experiments we've done, but I shall come to that again at the end of the talk. The centre of the atom is the nucleus, which is made of things called protons and neutrons. Here I have a rather enlarged, sophisticated model of a proton, and it's coloured sort of red to remind us that it's positively charged, and it's also big to remind us that it's actually big on the scale of an electron. In fact, an electron is less than 10 to the minus 18 meters in size, whereas a proton is 10 to the minus 15 meters, which is small to you and me, but it's 1,000 times bigger than an electron, so this is big on that scale. The proton is made of smaller bits and pieces called quarks, as we will see later. Okay, right. This is a sophisticated Royal Institution working demonstration model as used in the Christmas lectures. Unlimited budgets. So, as far as we know, the quark is an ultimate seed of everything. The size of a quark is less than 10 to the minus 18 meters. That's the shortest distance we can probe so far. Maybe in the next year we'll do better, and that's what I'm going to tell you at the end. So that's where we're going. How did we get there? Well, we got there, next slide please, originally courtesy of Ernest Rutherford, who, as a physicist, I suppose I have to admit, got the Nobel Prize for Chemistry. And he got the Nobel Prize for his discovery of the disintegration of the elements and the chemistry of radioactive substances, not for the discovery of the atomic nucleus or the structure of the atom, which is what many people think he got it for. He could have probably got more than one Nobel Prize if they'd been more generous. I want now to show you the basic idea of what he did. I think I may have shown this in a previous lecture in a different context, but it's a very beautiful thing, and I like to show it. It's how Rutherford actually discovered the idea of the atomic nucleus, and it really shows genius at work. Let's go to the next cartoon logo, which shows the famous idea. Thomson had discovered the electron, negatively charged, which showed that there were negative charges inside atoms. Something positive, therefore, must balance it to make atoms, which make you and me, overall uncharged. So where is the positive in the atom? What's the inside of the atom look like? So one possible idea was that the atom is a sort of uniform mush of negative and positive charge. And that's what this sort of cartoon is illustrating, sort of reds and blues all over the place. Now, Rutherford's insight was that if you fired atomic bullets at atoms, you could see what happened. Atomic bullets in this case are alpha particles. They are naturally produced, positively charged particles, which today we happen to know are the nuclei of helium atoms. But all you need to know for this, and all Rutherford knew at that time, was that they were positively charged and quite massive on the scale of things. So the idea was this: fire these things at atoms. If the atom looks like that, then these alpha particles will just sort of plough straight through, like going through a mist without very much happening. However, if the next slide shows us, if the atom has a positive nucleus at the centre, which we now know is, of course, what it's really like, then the alpha particles would, most of the time, on the periphery, just pass straight through. But occasionally they would get near the nucleus, have a lucky strike, and get deflected rather violently. And even, in the next slide, occasionally you would have a direct hit, and the thing would bounce right back. Now, that's actually what happened. I'm now going to show you what Rutherford did with that. But as this is really the critical feature that Rutherford used, and that we're still using today, let's make sure that we get the idea. The idea is this: you're firing some particles, in this case alpha particles, at an object, in this case atoms. And if that object is sort of extended and diffuse, nothing very much will happen. The beam will go through, it may get deviated a little bit, but not very much. If the beam suddenly violently gets deflected, it tells you intuitively that there's something concentrated inside there that's doing it. That's the general idea. That is what Rutherford did to discover the structure of the atom nearly a century ago. That is what we did 30 years ago to discover the structure of the proton, where we found that it had got hard centers. That is what we're doing today at this accelerator in Hamburg, to scatter off the quarks themselves to see if they are diffuse on the distance scales of 10 to the minus 18 or have got hard centers. And I will show you an event, as they call it, at the end, which is interesting. Okay, we'll leave that there in the background and think what it means. In a way, that is like a movie, in the following sense. The red blob here, the atomic nucleus, let's say the proton in hydrogen, let's use this as the model to demonstrate that. And I'll put it somewhere, like there. And imagine that I am the alpha particle, which is the thing shown yellow on there. So what is happening is that the alpha particle, me, has been shot from some radioactive source far, far away from that atomic nucleus. I'm positively charged, and that nucleus is also positively charged, and like charges repel. So I'm zooming in towards that, and the nearer I get to it, the more I start feeling the repulsion of the light charges. So I come zooming in, I come to a stop, and then I'm repelled out again. And that's what this cartoon here is illustrating. So it's a static picture, but actually it's a movie. The alpha particle yellow dots came in from far away, and out again. Having got that idea, let me now show you how, in 2 pages of illegible writing, Rutherford solves the structure of the atom. These 2 pages are photocopies of his original notes, which are stored in the Cambridge University Library, which is quite remarkable, seeing as he did this stuff at Manchester, that Cambridge University has managed to get them in their library, but as an Oxford person, I feel bounden to report on that. His writing is not the neatest. In a moment, when you see him excited, it will get even less legible. When I first saw these many years ago, I thought that I was going to be shown some leather-bound notebooks with gold leaf lettering on, you know, with Lord Rutherford of Nelson, OMFRS, Nobel laureate, and so forth, and was astonished to discover that I was presented with some sheets of loose leaf paper held together with a paper clip and written on in pencil. I mean, that's how real discoveries are done. Anyway, there is only one equation in this, you'll be pleased to know, and only one equation in this lecture, you'll be pleased to know. It's down here. And I'll read it out and see if any of you have any bells ring. It says half mv squared equals e squared over distance. Half mv squared is what we call kinetic energy. E squared over distance is what we call electrostatic potential energy. Let me just tell you what's going on. Remember the cartoon. The alpha particle far, far away is so far, initially, is so far away from the charged proton down there that it doesn't feel it. So its energy is totally energy of motion, kinetic energy. That's what we call half mv squared. As it zooms in towards that, it feels more and more of electrostatic repulsion. So it's losing its kinetic energy as it slows down and gaining the electrostatic potential energy of repulsion to keep the total energy balanced. Zooming until it momentarily comes to a halt. Now at that moment it's got no kinetic energy at all because it's at rest. The energy is now totally electrostatic energy of repulsion, which is the product of that charge, my charge, divided by the distance between us. So what Rutherford has done here is written down conservation of energy. He said when that alpha particle beam was far, far away, its energy was completely kinetic, half mv squared. When it came to a halt momentarily, its energy was totally electrostatic, the charge squared over the distance. I can now take the distance up here, the 2 up there, the mv squared down there, that's the higher maths that you need, and I can work out, by putting the numbers in, what this distance is. I get an idea of where the positive charge is. And so he turns the page and starts putting the numbers in. And you can see that it's the genuine article because he makes mistakes and he crosses things out. And as I always point out to school kids, this is long division. Which the sophisticated audience appreciate the joke. What I find terrifying is now that as you give this talk, you don't get the laughs anymore. The kids look there thinking, what's he talking about? Anyway, so Rutherford puts the numbers in, works out the arithmetic, and he finds that B, this distance of closest approach to the positive charge, is a number over 10 to the 12 centimetres, or of the order of 10 to the minus 15 metres. So by that simple thing, just thinking about the one that bounces back, and using conservation of energy, kinetic energy when it was far away, potential energy when it came to that stop, he's worked out 10 to the minus 15 metres as the distance. That's genius. Then he got his workers, Geiger and Marsden, doing the whole series of experiments, firing alpha particles at a whole range of atomic elements, and seeing the charge that they scattered through this angle or that angle and so forth, to give what we call Rutherford's scattering law. But the basic insight came from really getting, almost literally, to the heart of the problem. What happens that makes them go... And at that moment on this page, which is still blank because we're back here in 1911, you, Rutherford, have just written that number and you've discovered what we now call the atomic nucleus. And the excitement of the discovery hits you and your writing becomes almost impossible to read. It says, since probably radius of atom is of order 10 to the minus 8 centimeters. That's 4 orders of magnitude difference between these. It is seen that distance of approach to charge center is very small compared with radius of atom. I mean, this bit here, you can see the excitement, you can see the speed that he's writing, because it hardly deviates from a straight line. It is very small compared with, I mean, that is beautiful, that's remarkable. And the understatement of the century down here, where is it? B is an important constant from something or other, which I can no longer read. But yes, he discovered the atomic nucleus. That is lovely. So he has discovered the idea that at the center of, let's say, the hydrogen atom in particular, the simplest one, the positive charge is concentrated on what we now call a proton. And the basic thing that is used is the idea of firing beams of particles at atoms and discovering that they sometimes get violently deflected. In particular, come straight back. So if we now take that idea and move it on of the order of 60 years, we can imagine using electron beams and firing them at hydrogen to see what the proton looks like. Because by the 1960s, we had electron beams that had enough energy that their wavelength was small enough to be able to measure things of the order of 10 to the minus 15 meters. So can I have the next slide? Yep. And they discovered that the proton indeed had a size. They couldn't yet see what its innards were, but they knew that it extended over a range of about 10 to the minus 15 meters. So by 1970 at Stanford, they had built a more powerful electron accelerator. And this is where we ended last week. And I think I made an analogy with the Thomson tube by saying that this is like the back end of the Thomson tube, where the electrons are boiled off, but they're accelerated along the tube, in this case by 30 billion volts, all the way to the far end. And at the far end, there's a target of hydrogen, which is, if you like, essentially protons. And the electron beams, by then, have so much energy that their wavelength is much, much less than this size. So they're able to look, if you like, inside the proton. And it was from that they discovered that instead of the electrons scattering very, very gently, as you would have expected if the charge was uniformly spread over this distance, they scattered violently on the occasions when they had direct hits on what we now call the quarks, 3 quarks that carry the charge of the proton. So this is, in principle, exactly the same as Rutherford had done in 1910, but now being done at much higher energies, which means much smaller distances. Instead of looking at the atom as a whole and discovering the nucleus, you're now looking at its nucleus and discovering the quarks. Now, if I'm really brave, I think I can show... Can you just turn that off now, Jeff? Thanks. Yep, so this is the same picture you just saw, but just from a different angle. So this is the 2-mile-long electron accelerator at Stanford. This, as I said, was the back end of the tube. It's the far end where the target is, and it scatters off the target. You remember I said you need to have a beam onto a target and then a detector. Well, the target, when it's in place, is usually sitting on a table just here. The electron beam comes zooming in, scatters off the protons that are in the hydrogen of that target, and they get scattered through various angles. And this here is the special eye, the detector that was used to capture any electrons that came off at that angle. You can see here the scale of size of 2 people that are standing next to it. And again, here's the scale of a person compared to Thomson's tube. Here is the scale of 2 people compared to the detector, let alone the 3-mile-long accelerator. And that is what you need to be able to look inside the proton. So that is where, if you like, we were until a few years ago. Cover that for a moment or two to bring you up to speed. So this is the picture that we had from about 1970. But the proton, and a neutron as well for that matter, is essentially seeded by 3 quarks. And these quarks carry electric charge. There are 2 varieties of quark that we need to make protons and neutrons and the nuclei of all atomic elements. They're called up and down. They don't look like that. But anyway, the up quark carried, in units where the proton has got 1 unit of positive charge, the up quark has got 2/3 positive, and the down quark has got 1/3 negative. So to make a proton, it's 2 ups and 1 down. And you can also check that if instead of that you've got 2 downs and 1 up, the minus 1/3 twice would exactly cancel out the plus 2/3 and leave you with a neutron. So from this picture you immediately see that a neutron, which is the neutral analogue of the proton, actually has got charges buried inside it that just cancel out. So that although it's neutral on the 10 to the minus 15 meter scale, it's got charge inside. And indeed, the neutron has a magnetic moment, which is used in experiments at Rutherford Lab to probe the structure of materials because of its inner quark structure. So this, anyway, is the picture of the proton. It's 2 ups and 1 down. And here is a not to scale picture of a hydrogen atom. And you see that the negatively charged electron on the outside, on a distance scale of about 10 to the minus, 10 to the minus 10 meters or so, is balanced by the positive charge of the proton, which lives on 10 to the minus 15 meters, 5 orders of magnitude smaller than it. And that this charge is itself made from 3 little things, plus 2/3 and minus 1/3, which themselves actually live on a distance scale of 10 to the minus 18 meters. There's remarkable layers to this. I mean, to give you a feeling for it, the size of the hydrogen atom radius compared with the size of the proton in the middle, if you scaled it up, if the size of the hydrogen atom was like the longest hole at St Andrews golf course, about 500 meters long, then the proton is like the little hole you're trying to get the golf ball into. So that gives you a feeling for how empty, if you like, the hydrogen atom is. And then if I was to magnify up that little hole that you're talking about inside it, looking for things that are only 1,000th as big as it. So it's quite remarkable how matter is made. And we are made of matter. We are actually pretty much empty. Now you might ask yourself, how is it we're so solid? That's another lecture some other time. The other remarkable thing, though, which we do not know the answer to, and I'll just mention it here in case somebody has a good idea, is this. The fact that atoms, that matter is electrically neutral is quite a miracle, isn't it? That the negative charge of the electron, which, as far as we know, has nothing at all to do with quarks, exactly gets balanced by the positive charge of the proton. And the positive charge of the proton is coming about because there are plus 2/3 and minus 1/3 and 3 of them. I mean, what an incredible conspiracy. Now, if there had been 4 of them, it wouldn't have worked. Or if they'd had 1/4 charges and there were 3 of them, it wouldn't have worked. For some reason, they like to live in threes, and they each carry 1/3 fractional charges, so they conspire to make the plus 1 out of quarks. Meanwhile, way at the other end of the golf course there, whirling around, is a negatively charged electron, miraculously cancelling it all out. Something is going on here, and we don't know what it is. So you feel, you either hope you're going to have a brilliant idea that will write the answer down on a piece of paper, or, which is more likely, you have to have your face rubbed in the answer, and that's what experiment is about. But actually, as a theorist, I can admit the fact that most, if not all, of advances are made when experimentalists discover something we hadn't expected and point us in the right direction. And so that is what we're trying to understand. What is really going on? Is it the case that quarks are the end of the story? Well, before I tell you where we are with that, let me just give you this summary reminder of the scales of things like when we came in. Earth, and also to show you how empty matter really is. The solar system appears pretty empty in the sense that the size of the Earth compared with the size of the Sun, and in turn compared to the Earth's orbit, are factors of 100. The size of the electron orbit in hydrogen compared to its nucleus, and the nucleus compared to the electron or quark size, are factors of 10,000. So this picture that one carries around that, atoms are like miniature solar systems, are pretty empty. They're not. Atoms are incredibly empty on the scale of the solar system. I mean, the solar system's densely packed compared to what atoms are like. So what we would like to know, among many things, is are there things smaller than electrons and quarks. The first step along that is, do quarks have a size? I mean, we can measure down to a size of 10 to the minus 18 meters, and that's what we've done over many years by scattering off protons and scattering off these guys. Could we probe down to even smaller distances? Well, in principle, yes. I mean, all you have to do is to make a more powerful collision between electrons and protons. How do you do that? Well, you could build a bigger accelerator, but that thing I showed you was 3 miles long. The technology was developed in Germany about 10 to 15 years ago. I've shown you in other talks how at CERN we can take electrons and whirl them around a 27-kilometer ring, and positrons, their anti-particle version, the other way. That is relatively easy. The trick being the fact that electrons and positrons, which are matter and antimatter, have exactly the same mass but opposite charge. So with a single set of magnets, the magnets which will steer electrons this way around a curve will steer the positrons around the same curve in the other direction and bring them head on. What they'd done in Germany was to have electrons going one way around and protons, which are 2,000 times more massive, going the other way around to make them collide head on. And that's what the HERA accelerator is. And here's a picture down in the tunnel. I mean, it's a circular thing, but it's only going off around the curve rather gradually. And this is a bit of a messy picture, but it's the best one, I'm afraid, that I could have. That there's a set of magnets and things steering sending the protons in one direction, and a completely different set of magnets bringing the electrons along in the other direction. And then, at a couple of places around the circle, they're brought into head-on collision. So the idea is this: you bring them into head-on collision. For those of you who are train spotters and like numbers, the electron energy is about 30 billion volts, which is a similar energy that that 3-mile accelerator that I showed you earlier can produce. However, that 3-mile accelerator was firing those 30 billion volt electrons at a static proton. This is firing them at a proton which is coming the other way with 200 billion volts of energy. So it's a head-on collision. And you know what that'll do for you. If you hit a car, if you rear-end a car that's waiting at a traffic light, it's got its brakes off, I mean, you'll damage it at the end, but it'll recoil from you. So you don't have a big insurance claim. If, however, at the same relative closing speed you'd hit head-on, you have a disastrous insurance claim. And that is the power of head-on collisions. So that's what they do. And with these collisions, they can probe not just the protons, but they're able now to scatter off the individual quarks and see what happens. Now, if those quarks are, have a size of 10 to the minus 18 meters, we can calculate exactly how the electron beam should scatter. The probability that the electrons scatter through this angle or that angle or so forth is calculatable exactly. So you then go and do the experiment. And you do this billions and billions of times, and eventually, each one scatters at random, because quantum theory says you can't predict time by time what will happen. But if you do enough of it, you can statistically say what will happen. And you get what's called a distribution. And that is what they measured, and they found exactly the distribution that you would expect to happen if the quarks had a size of 10 to the minus 18 meters and there was nothing inside. Now, as you go down this distribution further and further towards the end, you're looking at the chance of there being ever more violent collisions. And then they got to the very far end, and after like about 10 million events in here, there was 2 or 3 that looked as if it suddenly had a little blip at the end. As if there was very, very rarely, once in a blue moon, a violent collision happened more than you'd expect. And I actually got a picture of one of these. You might be remarkable to realize that one can. So this is what comes out into the computer that's recording the events. The orange is, if you like, a cross-section through the detector. And I should explain here what is going on so that one can see why this is remarkable. The proton beam has come in from this end, and the electron beam has come in from this end through the center of the thing, and they've collided here. Now, let's think about the proton beam. Imagine you're a proton beam. As a proton, it's a complicated thing. It's got all these quarks inside and a lot of other force field mess that we'll talk about on another occasion. So when you get hit violently, you get smashed up into bits. And the bits fly out into the detector, and those are the red trails that you see down there. They're the shattered proton going off in that direction. The trail up there is the scattered electron. Doesn't seem very remarkable, but let's just think of this again a second. The proton beam with 200 billion volts is coming from this direction and been shattered, and it's carried on down there. Makes sense. The electron beam is coming from this end, hit the proton, and been turned almost back in its tracks. That is a 1999 analogue at the level of hitting quarks of what we saw Rutherford's backscattering and Rutherford's notebooks, that rare analogue of a head-on collision on an atomic nucleus. That's where 90 years have moved you. Now, this is the tantalizing thing. As they say, one swallow doesn't make a summer. That there's 10 million pictures I could have shown you where the electron beam here sort of went off. Oh, you can't see that, can you? No, you can't, sorry. The electron beam coming in here, you know, it goes off in this direction most of the time, and the further away you get an angle, the less the chance. And beyond here, you have to wait lots of times, you know, and then there's almost nothing, and then suddenly you get one back there and another one like that. Is this just the tail of a vanishingly small distribution, or is it the beginning of something big? I mean, it's the same game, you know, tossing a coin. You toss a coin 5 times, you might get 5 heads in a row, and that can be chance. Unlikely, but chance. If you toss it 50 times in a row and you get 50 heads, it ain't chance, it's telling you something. And that is the situation that they're in. It's like having tossed the coin, actually not 5 times, it's about 3 or 4 times, which isn't a big deal, but it's tantalizing enough. So what is happening is, the end of this year, the HERA accelerator is being what they call upgraded. It's not having its energy increased. What is actually happening is, if you like, that the intensity of the beams, the brightness of the beams is being increased. And this means that the chance, I mean, if this is a real thing, instead of getting 4 of these in 5 years of work, you'll get 40 of them in a year of work, if you're lucky. And then you will be able to tell whether it is just statistics fooling you, or whether you have indeed found that there's a structure inside the quark. In any event, what you will have done is moved the frontier of distance down from 10 to the minus 18 meters, which is where we currently are, to 1/10 of that. And who knows what the answer will be. So that is where we currently are. But it's very tantalizing because we don't understand why it is that electrons on the outside of atoms conspire to balance so perfectly with the quarks in the middle. It's as if they do know about each other somehow. And yet, they, in all our theories at the moment, are completely independent of each other. What's going on? Are electrons and quarks siblings in some profound sense? Don't know. But this might tell us something about it, and whether I shall be around here to tell you the answer is another matter. But, you know, watch out for this. Okay? Thank you.